Hey everybody, I am live and in stereo, or should I say we are live and in stereo. And today what we are going to do is we are going to largely focus on Hess's law, also known as Hess cycle, also known as the law of heat summation, right? There are multiple names for it, but we really care about how we can solve questions for Hess's law and through Hess's cycle, and what was the importance of Hess's law, right? I'm going to write it down, and first we are going to look at some boring definitions and boring theories and boring stories, and then we're going to start off with our actual calculations. Right now, what exactly is Hess's law? He basically just cheated off something from the first law of thermodynamics. What's the first law of thermodynamics, everybody? We've covered it a billion times. You've been studying it through your elementary schools as well, elementary classes as well. What's the first law of thermodynamics? It's energy can neither be created nor destroyed. It's just converted from one form to another, right? So that's the first law of thermodynamics, and that's literally what Hess is just copied stuff from, right? It's energy can neither be created nor destroyed. And his entire law, which we know as Hess's law, it's based on the first law of thermodynamics. He came up with this about, I think, if I'm not wrong, it was about 1839 to about 1842. It took him almost 3 years to come up with this. He first called it the law of heat summation. It was first known as the law of heat summation. So if you are giving an interview for your universities, some interviewers call it the law of heat summation or the law of summation, but largely speaking, it's called Hess's law, right? Now, it was a hypothesis before, but obviously hypothesis is testable, right? So after we scientists tested it on a lot of experiments, a lot of equations, a lot of experiments, it held true. So it changed its status from a hypothesis into a law, right? And now what exactly did Hess say? Hess basically said that, if you have enthalpy change, for any chemical reaction, so the enthalpy change for any chemical reaction is independent of the route that it takes. I'll first write it and then I'll explain it, right? So it's independent of the route, or you could say it's independent of the number of steps taken. It's independent of the route or the pathway taken, or it's independent of the number of steps taken, provided that the initial and final conditions remain same, provided that initial and final conditions stay same, and final conditions stay same, right? Now, what exactly do we mean by this? Basically, he copied stuff from the first law of thermodynamics, right? Which is what? That energy is neither created nor destroyed, right? So it's the law of conservation of energy, aka the first law of thermodynamics, which basically tells you no matter which route you take, it's gonna be your enthalpy change is gonna be independent of the pathway that you take. It's going to be independent of the route that you take, provided obviously all the conditions remain the same. You don't change anything on your own. You don't make a change to the system, right? And to put it in very simple terms, he basically said that, hey, if A goes into, let's suppose D, if A goes into D directly, and I call this X, right? If A goes into D during a chemical reaction, A goes into D directly. A can also go into D before going into D. It can go into B, B can go into C, and then C can go into D. And he said, hey, that if A goes into D, let's suppose I call this, the enthalpy change is X right here, then and let's suppose A to B is Y and B to C is Z and C to D is E, whatever, right? Now he's saying if A goes directly into D, the enthalpy change is gonna be equal to if A were to go into B, then go into Z, then go into E, right? So he said, hey, that it's pretty simple. It's just law of heat summation. It's basically saying that if you move from Lahore to Peshawar through a direct route, and then you move from an indirect route, the energy that you are gonna the energy, that's the overall energy change, is gonna be equal to each other. Direct route is gonna be equal to indirect route, and that's what he's saying. He's saying the enthalpy change for any chemical reaction is independent of the route that you take. You can take a direct route, you can take an indirect route. It doesn't really matter, and that's what law of conservation of energy also says, or the first law of thermodynamics says. Energy is conserved. No matter which route you take, energy will in fact be conserved, right? So let's suppose A were to go into D, again, A were to go into D, and that's a direct route, sir. And I can say, hey, A can also go into D by going into B first, and then this B goes into D, right? Now, what I mean by this is, hey, if A goes into D and the enthalpy change is X, and A goes into B, the enthalpy change, let's suppose, is Y, and B goes into D, the enthalpy change is Z, X would be equal to Y plus Z. That's why it's called the law of summation. The direct route, see, this is the direct route. Tuck, 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 tuck. And this is the indirect route that you could take. You could go from A to B first and then B to D. Or you could go directly from A to B. But the idea is that A to D would be equal to going from A to B first and B to D first, right? So that's why I'm saying, hey, the enthalpy change right here is equal to the enthalpy change here and here. So X equals Y plus Z. Right? You add these two, that'll be equal to X, right? So that was the basic idea for it. Now the question is, why did we need Hess's law? What was the need for it? Why couldn't you just perform experiments? Because we realized that, hey, in certain experiments, you can't figure out the enthalpy change. You can't directly figure out the enthalpy change. Certain experiments are such that you cannot actually practically perform those experiments. Or you cannot measure the enthalpy changes for those experiments. And so a creative way was required. And that creative way is effectively Hess's law. Let's suppose there's a particular experiment for which I want to figure out the enthalpy change, which is A going into D. And I can't figure this out. But I know that A can go into B and B can go into D. And I can measure this. I can't measure this, but I can measure this. So I'm saying, hey, A going to B, B going to D. These two should be equal to the direct route. That's it. That's how easy the idea of Hess's cycle is. Literally, that's it. That's basically a very creative way to figure out enthalpy changes which you can't directly find, right? And your books has certain definitions as well. My definition is this, and I like you guys to write this in the Cambridge exam as well. But your book also has, a lot of books, not just one book, but a lot of books have a lot of definition for Hess's law. Some books also define it like this, and this is only for MCQ purpose. Before we move forward, give this a look. Well, see, the total enthalpy change in a chemical reaction is independent of the route that you take, as long as the initial and final final conditions are the same, So you'll see a lot of these things written in books different way, in different manner, but obviously you need to understand that it can be tested like this in the MCQ, it can be tested like this in the MCQ. The idea is the same. It's independent. The route, no matter which route that you take, the enthalpy change is independent of the route, right? And so, which particular experiments were you not able to figure out the enthalpy change for? Which particular experiments? Sir, one of the best example that I can give you guys is the formation of carbon monoxide, right? This is one of the best examples I can give you, because we realized that, hey, when carbon reacted with oxygen and gave you guys carbon monoxide, you could not figure out the enthalpy change for this reaction directly. Now, you can't perform any experiment to figure out the enthalpy change of this particular reaction, which is obviously an incomplete combustion. And this carbon is obviously graphite, right? And we know why it's graphite. In the last classes, we discussed this in quite a lot of detail. So the idea is that I can't figure out this enthalpy change out directly, right? And frankly speaking, in your school labs, or even in sophisticated labs, you can't figure this out. No, you can't find this out, right? But you realize that if I take carbon and I react it with oxygen, and the oxygen is in excess, and it gives me carbon dioxide, this enthalpy change I can figure out. I know this enthalpy change. This enthalpy change of graphite right here is about negative 394 kilojoule per mole. I can figure this out. I can figure this stuff out. Right? and not in your school labs. Please understand, your school labs can't figure this out for you. Nah, you don't have enough sophisticated labs. The school labs aren't enough sophisticated for this experiment to take place and for them to give you guys the enthalpy change. Nah, you can't. It's in more sophisticated labs that you figure out this enthalpy change. And frankly speaking, you can also figure out the enthalpy change of combustion when carbon monoxide burns in oxygen and gives you carbon dioxide. You can even figure this out. And this is in fact the enthalpy change of combustion, the standard enthalpy change of combustion. It's when 1 mole of any substance burns, right, in excess oxygen. That's called the standard enthalpy change of combustion. Under standard conditions and standard states, we all know that stuff. But that's the enthalpy change, and you can figure this out. And for this fella, the enthalpy change is about negative 283 kilojoule per mole. Now the question is, can we use these two? Can we use these two to figure out this enthalpy change? The only way we can do that is through Hess's law or Hess's cycle. And here is where the fun bit starts, right? Here is where the fun bit starts. Sir, I have a question. Why can't we figure out the carbon monoxide's enthalpy change, carbon reacting with oxygen to give you carbon monoxide? The answer to that, kiddo, is not going to be tested in your exams. But the reason why you cannot directly find it through an experiment is because whenever carbon reacts with oxygen, even if it's limited oxygen, even listen, this is very important, even if it's limited oxygen, it will form some carbon dioxide. It'll always form certain amounts of carbon dioxide, even if it's limited amount of oxygen. How good is that? How fun is that? And this particular reaction is unavoidable. It's an unavoidable reaction. Avoidable. So even if there's limited oxygen, even then some carbon dioxide forms, and that's unavoidable. That's why you can't directly figure out the enthalpy change when carbon monoxide forms. Nah, you can't do it. Because when you're performing this experiment, carbon dioxide also forms even if oxygen is limited. How fun is that? You know? And this is an unavoidable reaction that takes place. So this will cause error. You can't directly find it out. What do? We use creative ways like the Hess's law, right? Or the Hess's cycle. So I'm going to write stuff for you. So I'm going to write it. We know that the enthalpy change of combustion, we have the enthalpy change of combustion of carbon monoxide. We have the enthalpy change, the standard enthalpy change of combustion of like graphite, which is carbon. And that's equal to, and these two are equal to what? One is equal to minus 283 kilojoule per mole. And one is equal to minus 349 kilojoule per mole. Right? Now we know why we are using Hess's law, because the idea is we can't find this directly and we'll have to use an indirect method, and that's where Hess's plays a very pivotal role. He says the enthalpy change for any reaction is independent of the route that you take. So I can take another route, an alternate route, to figure the enthalpy change for this particular reaction A. Right? So I'm going to write this stuff. Now the first things, in the first 5-10 minutes, I want to build your basics. So please just follow my lead. Right? Can you guys write the reactions for these two? Can you guys write the enthalpy change of combustion of carbon monoxide? What is that? When carbon monoxide reacts with oxygen to give you carbon dioxide. That's the enthalpy change of combustion of carbon monoxide, where 1 mole of carbon monoxide reacts with oxygen to give you carbon dioxide. And I've written it here, right here. Carbon monoxide reacts with oxygen, gives you carbon dioxide. Similarly, can you guys write the standard enthalpy change of combustion of graphite, which is what? Graphite burning. 1 mole of graphite burning gives you what? Carbon dioxide, right? And the enthalpy change here is minus 283 kilojoule per mole. And the enthalpy change here is minus 394 kilojoule per mole, right? Now, the idea is that I need to figure out what is the enthalpy change when carbon reacts with oxygen to give you carbon monoxide, right? This is the idea. This is what I want to figure out. I don't know this. For this, I call it, this is an approach which is widely used in universities, right? And this is the most beautiful approach towards it. I call this the love triangle approach. Although I'm going to use Hess's cycle, but I call this approach the love triangle approach. Right? Now, how do we figure this stuff out? I know 2 enthalpy changes, and I need to figure out this enthalpy change right here. Now, how do I do this using Hess's law or Hess's cycle? How do I do this? Well, the idea is to know how to use the love triangle approach. Triangle means there must be 3 boxes that I'm going to draw. And these 3 boxes are very crucial for me. For now, first understand the method, and then you will also understand why I'm doing this. So I'm going to draw 3 boxes, and I'll call one box as my start, the next box as my end, right? Now, what do we mean by start and end? Basically, I'm going to start the reaction from one point, right? I'm going to take a starting stage. And which reaction should I take as my starting stage? Should I take this reaction as my starting stage? Should I take this reaction as my starting stage? Should I take this reaction as my starting stage? Or, and for ending stage, should I take this reaction as my ending stage? Should I take this reaction as my ending stage? And should I take this reaction as my ending stage? The answer is pretty simple. See, I'm going to be given these 3 equations. And this is, frankly speaking, this method that I'm going to teach you right now, it's my own way. And I've been doing this for quite a lot of years now. I've also trained some teachers on this back in the day. But I'll teach you, right? So how do you select your starting stage? See, I'll select my starting stage with the idea that all arrows are going away. Starting stage should be that stage where all the arrows are going away. And ending stage should be that stage. This should be the starting stage, right? This is how start should look. All the arrows should go away from it. And the ending stage is the stage where all the arrows converge to it, right? All the arrows end there. All arrows end there, right? Now, how do I know all arrows are going away? And how do I know all arrows are ending? How does it help me select which equation? How does it help me select the equation? It's very easy. See, you look at your reactants, right? And you're going to see here, you're going to ignore oxygen. They're all the same in all these experiments. And I'm going to look at carbon monoxide, carbon. Which of the reactant is repeating the most? Which of the reactant is repeating the most? Carbon monoxide, carbon, or carbon? It's carbon. Carbon monoxide is here, but carbon and carbon are repeating. So my starting stage should be from carbon. This is my starting stage, right? Carbon is my starting stage, because it's being repeated the most. Compared to these 3, it's being compared to carbon monoxide, carbon is repeating the most. And the end stage, which should be my end state? On the right side, I'm seeing carbon monoxide, carbon dioxide, and carbon dioxide. Which one should I take right here? The end stage. Carbon monoxide or carbon dioxide? Well, because carbon dioxide is repeating the most, it should be the end stage. So carbon dioxide is my end stage, right here. Right? So end stage is carbon dioxide and the start stage is carbon monoxide. Right? And what's the middle stage? This is called the intermediate stage. The intermediate stage or the middle stage. Which one is your middle stage? Well, the middle stage is what's left. It's carbon monoxide. And now you just draw arrows, right? I'm going to say, hey, I'm going to go from carbon to carbon dioxide. How do I go from carbon to carbon dioxide? That's my second equation. See, carbon reacting and going into carbon dioxide. Which is this? What is the enthalpy change here? That's minus 349. Minus 349 kilojoule per mole, right? And then I'm going to say, hey, I'm going to draw an arrow like this. I'm going to say carbon going into carbon monoxide. How is carbon going into carbon monoxide? Right here in the third equation, carbon is going into carbon monoxide, right? And this, I don't know. Carbon going into carbon monoxide, I don't know this stuff. Right here, I don't know this. And then carbon monoxide going into carbon dioxide. Right here, carbon monoxide going into carbon dioxide. I know this stuff. That's minus 283. Why I've written minus 28? That's minus 283. Minus 283 kilojoule per mole, right? Carbon monoxide going into carbon dioxide. So let me write this. Carbon monoxide going into carbon dioxide. What is that? That's minus 283. And your arrows are always going to be like this. Always. And this is now so simple. It's so simple. See, this is my direct route. Carbon going into carbon dioxide. And this is my indirect route. Carbon first going into carbon monoxide and then into carbon dioxide. And Hess said what? Hess's law of summation says, or Hess law of heat summation, whatever you want to call it, he's saying direct route equals the indirect route. What's the indirect route, sir? X plus, I'm going to add them, X plus minus 283. Right? I'm adding them, but this is negative, so I'm going to add this, plus, and then put negative in the brackets, And so how can I figure out X? X is minus 349, shift this there, plus 283. And x equals, what is x? Can somebody help me? Can somebody calculate it for me? Yeah. Kuruturan, I'm just not writing the, this phi here. You're right. I'm not writing phi everywhere. You can write it now. I just don't care about it. We know there it's under standard conditions and standard states, whatever. What do we get, sir? We get minus 66 kilojoule per mole. And all the questions would be solved like this. Every single question, you just need these three boxes, which I call the love diagram, right? And understand that it's very easy to select equation. See, in this first case, when carbon is going into carbon dioxide, which equation am I selecting? I'm selecting equation 2 right here. So this is equation 2, which I've selected. You can also write oxygen here. It's up to you. I don't like to write it. You guys can write it. And you should write it effectively. You should. But I want to make this crystal clear for you. So I've selected equation 2 right here. And then carbon monoxide going into carbon dioxide. See, carbon monoxide going into carbon dioxide. This was equation 1 that I selected. You can write oxygens if you want. And this is which equation that I selected. Carbon going into carbon monoxide. Carbon going into carbon monoxide. This is equation 3, which I selected. All the arrows are going to look like this. And now it's just time to practice. Practice will make you guys perfect. For example, I say, hey, there's A going into B, and then B goes into C, and then A goes into C, right? Can you guys figure out the enthalpy change of A going into C, given that the enthalpy change of A to B is minus 40 kilojoule per mole? And this enthalpy change is like plus 15 kilojoule per mole. And now you'll see how good you are at this. Again, I will draw my three boxes always, and I've drawn them. And what am I going to do? I'll say, hey, which should be my starting stage? Starting stage should be the stage which is being repeated the most, from which all the arrows are going away. And end stage is the stage where all the arrows are converging, right? So start state between A and B, which should be my start stage? A or B? A or B? Shabash, select. A or B? A is repeating most, so A is my start stage. Done. What's my end stage? End stage B or C? B or C? Which one should be my end stage? Shabash. Now it's just a piece of cake. C. So it's basically, I'm going to put C here, I'm going to put A here, and B would be my middle stage. Then I'm going to go like this, then I'm going to go like this, and this. 3 arrows, that's it. So the first arrow is A to C. A to C is this fella right here. I don't know this shit, right? The second arrow, A to B. A to B is this right here. Equation 1, 2, 3. So A to B is equation 1, right? I know this shit. That's minus 40. And then B to C, that's also given, plus 15. That's literally it. Can you guys calculate it? See, the direct root is equal to the indirect root. So x equals minus 40 plus, and I write this in brackets because it's law of summation. You actually sum it up. You sum everything up. So plus 15. Right? What do you get? Minus 40 plus 15. That gives me what? Minus 25 kilojoule per mole. Let me bring some complexity into it. That's literally it. That's all there is to Hess cycle. Don't worry, I'm going to teach you guys a lot of stuff. Don't worry. It's pretty basic, isn't it? Sir, I swear to God, this is so easy. Yes, I know. I just think, isn't it minus 394? What is minus 394? 349? Forget about it. 349, 394. If I've written 394, it's 394, 349. The idea is to understand the concept. You can change the values if you want. The values may also be flawed because I am making them on my own. So yeah. Sir, why was I stressing over this shit? I don't know, Aliza. You tell me. Next, let me make it a little complicated for you. And this is where the idea of flipping comes into play. A goes into B, and B goes into C, and C goes into A. And my question to you guys is, don't take help from the above example, please. This A to B is minus 40 kilojoule per mole. That's the enthalpy change. B to C is about plus 15 kilojoule per mole. And this I don't know. Now, how am I going to do this? Well, the same idea. Draw my three boxes. Let me make this go down a little. Draw the three boxes. And now let's come back. Which should be my starting stage? Now, here is where things get fun. Yes, iPad, you'll get the notes. You'll get it. Relax. Okay. So here is where things get fun. Should I take A as my starting stage, B as my starting stage, or C as my starting stage? This is where we all are left in awe. This is where confusion starts to overwhelm us. Sir, which stage should I take? Which should I take? What should I take as my starting stage? This is my start. Start should be the one that's being repeated the most. Here, A, B, C. Which should I take? Let's just, I don't know. They're all being repeated once. Can I not flip an equation? I can flip an equation, can't I? What if the examiner has given me this stuff and I flip it out? Which means that A goes into B and then C goes into A, and I can, it's your choice, whatever you want to flip. But I'm going to flip equation 2. And I'll tell you why I'm flipping it. If I flip this, it'll be C going into B. Isn't that? And once I flip this, this is no longer going to be plus 15 kilojoule per mole. It's going to be minus 15 kilojoule per mole. Isn't it? And this is minus 40 kilojoule per mole as it is. Now, is it back to square? Are we back to square one? Are we back to square one? What should I take as my starting stage? C is being repeated the most. So I'm going to put C here. What should I take as my ending stage? B or A? B. That's it. You can switch number 1 as well. It's up to you. So you can take B as your ending stage, and then this is A. Now again, C will go from C to B. Literally you need, and in practical life, these are the diagram. These 3 boxes are what is drawn, and that's it. Even if you go on to pursuing PhD in chemistry, these 3 boxes are all you need to solve any Hess cycle question, right? So C to B. C to B is what? C to B. C to B is what? Minus 15 kilojoule per mole. And what is C to A? C to A, X, that's X, I don't know. And then A to B is minus 40 kilojoule per mole. So what is Hess law telling us? It's saying the direct root equals the indirect root. So direct root is minus 15, indirect root is X, and then plus its summation. Please be very careful. Don't put X minus 40 directly. Nah, it's X plus minus 40, right? That's why I'm using brackets. So minus 15 equals X minus 40. X equals minus 15 plus 40. What do we get, sir? What do we get? The same idea. Plus 25 kilojoule per mole. Acha. A student is saying, sir, no. I want to flip equation 1. Okay, do it. It's up to you. If you want to flip equation 1, it'll be the same answer that you're going to get. See, I am gonna flip equation 1 now. So I'm, instead of going from A to B, I'm going to flip it. I'm going to say, hey, B to A, right? And if you flip it, then this will also flip. Remember, when you flip an equation, the enthalpy change flips. So now it's plus 40, right? And B to C is plus 15. I'm not flipping this. That's as is given in the question. That's plus 15. And C to A, that's X. Sir, again, 3-box diagram, that's it. The love triangle, right? So what should be my starting stage? B. What should be my ending stage? Yeah, starting stage is B. Ending stage is what? A. This should be my ending stage. A is being repeated the most. So B is the start stage and A is the end stage. And in between you have C. So B to A, A to B, B to C, and C to A. B to A is what? Plus 40. Calculate it, you will get the same answer. I kid you not. B to C, plus 15. And then C to A, that's X. Let's do this shit. So plus 40 equals plus 15 plus X. X equals plus 40 minus 15. What do you get, sir? Again, plus 25 kilojoule per mole. Whatever you do. So used to watching your lectures in 2.5, normal speeds sound like slow motion. How easy is it, guys? Literally. Piece of cake. Let's move on to more difficult questions. And again, the questions that I'm doing right now at this point in time, rarely tested on your exams, but they are tested. Rarely tested, but they are tested, right? So question 3, right? For example, you have BRF. And please, I may be wrong with my enthalpy change, values that I give you here because I'm making them out. Some I know, some I'm making out. You need to focus on the method, right? So, they're not real values, most of them, right? Okay, chalo. BRF plus 2F2 gives me like BRF 5, right? BRF plus F2 gives me BRF3, and then like BRF3 plus F2 gives me BRF5, right? And this enthalpy change, I don't know jack shit about this. Don't know. But this enthalpy change, I know. It's minus 242. And this enthalpy change, I know that's minus 158. right? Now, can somebody calculate this? Can somebody calculate this? Let's do this. Pretty simple. Just need to insert the 3 boxes. And after this, I won't even insert these boxes. You can imagine these boxes exist. I'll just put the start stage here, the end stage here. Try to do it on your own. And this is the intermediate stage. Start stage. What should be my start stage? BRF, BRF3. BRF, BRF3. Anji, what is being repeated the most? This is my own method. I've come up with this. BRF, select it. That's why I thought I'd teach you guys this. BRF. And then, so this is my start stage, BRF. Again, please understand that it's actually BRF reacting with F2. You can write F2. You can write F2 here. I just don't care about it, right? And then, what's my end stage? BRF5 or BRF3? End stage. And now you start to see patterns. It's like solving a pattern paper, and this is BRF5. That's it. And the middle stage would therefore be what? BRF3. That's what's in the middle. And that's it. BRF to BRF directly and then indirectly. These are the literally the 3 box diagram that you need, right? So BRF to BRF5. This I don't know. See, this is X. And I've effectively, what I've done is in this start and end, I've selected the first equation. See, this is the first equation which I've selected. You can write plus 2F2 here. This is effectively the first equation. That doesn't mean, if I'm not writing F2 here, that doesn't mean that it doesn't exist. It does exist, and I'm actually selecting BRF to BRF5 is the first equation. So you could write this here. It's up to you, right? It's up to you. I don't like to write it, but it's there, right? And BRF to BRF3, that's what? BRF to BRF3, that's minus 242. And BRF3 to BRF5, that's here, that's minus 158. And I've seen people stressing so much on this. So direct root equals the indirect root. X is equal to minus 242 plus minus 158. Please always, it's the law of summation. So plus sign is there, needs to be there. Minus 242 minus 158. What do we get, sir? What do we get? Minus 400. And I promise you, if this question is done in the classrooms, you will see how long you will take on this question. It's piece of cake, isn't it? Fatma, just wait a moment. We will cover everything. I'm first going over these technical questions. We'll cover all the shortcuts as well, all the shortcuts. What if I want to flip this out for you? What if I want to, make this question a little more technical? Let's see whether you guys can do it. I'm doing all the questions in this one marathon class. I will be covering the entire Hess cycle in this class. Every single question, so that you guys don't have to do anything on your own. Just be present in the class. Plus 2F2. Let's suppose this is like, goes into BR5 or BR BR. 2F2 goes into BR5, and this enthalpy change is about, I don't know, right? And then BRF3 goes into BRF plus F2, and this enthalpy change is plus 42. And then BRF5 goes into BRF3 plus F2, and this enthalpy change is, let's suppose, plus 158. Do it. Shabash. Can you guys do it? Now I'm stuck. What should I take as my starting stage? And the idea is flipping it. And good books also, have written this, but yeah, that's it. Do it. Let me first answer Shifa's question. Shifa is saying, why aren't we taking F2 as our intermediate? No, Shifa, it's basically me writing equations. See, you could write 2F2 here. This was equation 1, right? I'm taking up equations, right? So BRF plus 2F2 gives me BR5. This is the first equation which I've taken. BRF plus F2 gives me what? BRF3. And then this BR3F3 plus F2 gives me what? BRF5. So it's basically I'm taking equations. It's not just taking this individual thing. I'm taking equations, but I'm ignoring this fella right here. ठीक है, Shifa? I hope that it made sense. You have this stuff. I'm just ignoring F2s. I'm actually taking equations, not these individual chemicals. Understand, please. I'm taking equations, not chemicals. Faris, this is the first equation which I took. The first equation. The second, see, the first equation which I took was coinciding. This was my start and this was my end. Right? Similarly, this equation here here BRF, but it doesn't coincide with the end. That's why I took the start and end as the first equation, right? And then what I did was the end is BRF5. It's gonna end. It's gonna all converge on BRF. All the arrows are gonna converge on BRF5. And see, BRF is the start state because all the arrows are going away from it. But the F2s are there. It's actually the equations that I'm taking. I just can't be bothered writing the F2 over and over again. Make sense? Okay. That's why I ignore them. You can also. It's permissible in the exam, unless they specifically say so. Okay, try to do this. Okay, let's see whether you guys are right. Now the problem is I need to figure out my start stage. The only thing about Hess cycle is to figure out your start stage and to figure out your end stage. Now which stage is my start stage? Which equation should I flip, right? Now the idea is, see, if I flip this equation right here, if I flip this equation, the second equation, BRF would fall here. My starting stage would be BRF because that's the most, that's appealing the most. And BRF3 would be my ending stage. So awesome. I'll just flip equation 2. And remember, when you flip the equation, this sign also flips, right? So let me flip it. Let me write this equation again. BRF plus F2 gives me BRF3. I flipped it, so the enthalpy change also flips. And that gives me plus 242 ki jagah, it'll be now minus 242, isn't it? And the above equations are as is. So BRF plus 2F2 gives me BRF5. And that's X. I don't know that shit. And then BRF5 gives me I'm writing down the two equations all over again. BRF3 plus F2. And it's one of my favorite chapters because it's so easy. I don't know why they've made it so complicated. And this is plus, the enthalpy change for this is the same, plus 158. I haven't flipped it, done anything to it, right? So let's do this. Start would be my BRF, and that's start. And end should be what? End should be BRF3. So effectively what I'm doing is end should be BRF3. Effectively, I'm taking the second equation because see, the start and the end are both coinciding. So this is basically the second equation which I'm picking up. But I don't like to write all the chemicals. These chemicals are present. Please understand, these chemicals are present. If you want, you can write it. You can write BRF plus F2 gives you BRF3, and we are going to do it later on as well. So BRF going into BRF3, right? And BRF5 therefore is my intermediate. Doesn't make a difference. So BRF to BRF3, tuck, and tuck. That's it. So BRF to BRF3, what's the enthalpy change? BRF to BRF3, that's minus 242. Minus 242. You should all be getting the same answer as before. Yes, you are right. And BRF to BRF5. BRF to BRF5, that's X. I don't know that shit. So X. Yeah, sorry for my language, girls and guys. And then BRF5 to BRF3, right here, BRF5 to BRF3. What is that? BRF5 to BRF3, that's plus 158. So minus 242 equals the indirect root, X plus 158. And that is X equals minus 242 minus 158. What does that give me, sir? You should all get minus 400 all over again. Maza aa raha hai? I'm just proving stuff to you guys. It's a piece of cake. Tuck. Any other questions? Done? You can, sir, can't we flip the third equation? That's a very good question. I don't want to look into it, but if you want, let's discuss this. See, if you have this particular equation and you want to flip the third equation, you can absolutely do this. BRF3, flip it. BRF3 would be your starting point and BRF5 would be your ending point, but then you would flip this sign as well and you'd get the same answer. Why not? Same answer. Same answer. Again and again and again. So if you flip any equation, will we get the same answer? Yes, Ahmad, you will get the same answer. I'm not saying, see, the examiner can test you like this. It's just, I'm giving you guys different testing techniques. The examiner can test you like this, where you won't be able to figure out which one is your starting stage. For that, you need just flipping. And I want to prove to you guys, no matter how many times you flip or unflip, you will get the same answer, right? So the examiner, it's just different techniques. The examiner can test you like this. The examiner can test you like this. You know it's the same answer because I've given you the same question over and over again. So you know it's the same answer, but the examiner will test you like this. How did you know it's the same answer? You don't know what the previous question was, right? Here you guys knew the previous question. Here you wouldn't. It would just be a question that would appear like this in front of your in front of you guys, and you'll be able to solve it. Just flip it out. Done and dusted. How easy is this? Literally, how easy? Do you want me to give you another one? NO plus, before we go into shortcuts, MO plus half O2 gives me NO2, right? And like N2 plus half O2 gives me N2 plus half O2 or plus O2 gives me NO2 right here. And then and this is half. And then you have N2 plus O2 gives me NO, right? And this is like half and half. The enthalpy change here, and the enthalpy change here. Do it on your own, guys. This enthalpy change is, I don't know. This enthalpy change is, let's suppose, plus 33, and this enthalpy change, let's suppose, is plus 90. Please realize that if you search them up in Google, you might not get the same answer, because I am making these values out. Some of them are flawed, some of them are not flawed. I don't care, I don't care. My idea is to teach you guys this. Please don't search it. What's the enthalpy change of this going into this? Probably whatever you find here would not be the answer for it, because I'm just making these values out, most of them. ठीक है ना? So solve it. Let's see whether you guys can solve it. Shabash, do it. Okay, so a lot of you are getting minus 57. Let's see. So which one should I take my starting stage, NO or N2? N2, obviously. What should be my ending stage? NO2, right here. So which equation should I pick? See, the start and the end for which it coincides, this would be the equation that you would pick. See, the start and end both are coinciding, and this should be your equation 1, right? So I'm gonna add my boxes. And it's up to you. See, like Mahad was saying, sir, why aren't you taking O2? Mahad, I am taking it. I'm just not writing it, This is the equation that I'm picking out. Nitrogen goes into NO2, right? This is the equation, the second equation that I've picked out, please. Right? And this is plus 33. I'm writing oxygen so that those who are confused can fix their confusions, right? And here the intermediate is NO, which is left, right? So NO, right, that's left. And NO plus what? NO plus half O2. You can write it. I'm not forbidding you guys to do it. You can do it. You can write it like this. It's up to you. Write it if you want, right? So the first equation, N2 going into NO2. It's just less clutter for me, right? N2 going into NO2. That's less clutter. That's plus 33. N2 going into NO. N2 going into NO. That's plus 90. That's plus 90. And then NO going into NO2. NO going into NO2. That's X. That's unknown. So direct root equals the indirect root. So plus 33 equals the indirect root. Plus 90 plus X. Law of summation. Plus 33 minus 90 equals X. What is X? X equals minus 57 kilojoule per mole. That's the enthalpy change for this reaction right here. This one. So I'm actually taking oxygen, I'm actually taking fluorine. I just don't like writing it. It's more clutter when I write it. You can write it if you want. See, you can write it. There's no harm in it. Right? Now you got it, Mahad. Done. How easy is this shit? Acha. Do you want me to test your guys' concepts of enthalpy change of formation, which I've taught you? Let's see. Here is, I'm going to test. See, before all of this, I'm just writing enthalpy change, I'm not writing formation, combustion, anything with it. But what if I say, hey, ClF3 reacts with F2, that gives you ClF5, right? And then Cl2 plus F2, and that's, I'll put like 3 F2s here, and then that will give me 2ClF3, right here, that's 6, and then that's okay. And then it's Cl2 plus 5F2, and that gives me 2ClF5, right? And now this is where I want to test your concept. Thoda sa, let me, those of you who have not taken yesterday's class, you will find it difficult because you don't know what enthalpy change of formation is. And frankly speaking, if you know it, then that's good. So enthalpy change of formation for ClF3 is minus 328 kilojoule per mole. Now I'm specifying, right? Enthalpy change of formation of ClF5 is what? It's minus 510 kilojoule per mole. Remember, enthalpy change of formation is for 1 mole. That's the only hint I'm going to give you guys. Remember yesterday's class? It's for 1 mole of this forming. That's the energy. For 1 mole of this forming, that's the energy. I want you to figure out this on your own. Shabash. The idea is the same. The same idea. Tuck, tuck, tuck. Maza aa raha hai? Chalo. Start. End. Sugoi. Right. What is start? Start should be which equation? Chlorine is here and ClF5 is here. So this equation 3 should be my start. Now it's up to you, Mahat. If you want to write 5 ClF2 with it, it's up to you. You can. I'm not stopping you from it. You can write 5F2 here, gives me 2 ClF5. It's up to you. I couldn't care less, right? But I'm not going to write it like this. I'm going to declutter my pain. So it's ClF5 forms here and here. This would be left behind this equation, so that's ClF3. Now, this is unknown. Cl2 to ClF5. Sorry, that's known. That's known. Cl2 to ClF5. That's known. What is this, by the way? Cl2 to ClF5. What is this? Shabash. Yesterday's class is important for this now. You are given the enthalpy change of formation. You are given the enthalpy change of formation of ClF5, which is what? It's for enthalpy change of formation is for 1 mole of ClF5 forming, isn't it? I'm not going to go into the definitions for it, but you know the idea. It's for 1 mole of ClF5 forming, 1 mole ke liye, right? And I've specified it, that it's formation. I've specified it right in front of your eyes. So if I've specified it in front of your eyes, oh, you guys tell me, if this is for 1 mole, how many more do you have right here? I have 2 moles. Sir, please show question. Oh, see the question. My God. Kill me. I want to die. No, I'm joking. Don't kill me, please. Use your brains. Use your brains. No, Aisha, I'm not labeling it yet. Whatever we were doing, it was just enthalpy changes. Enthalpy change, enthalpy change, enthalpy change. That's it. I wasn't putting any labels there. Right? So the reaction may be equal to combustion. It's up to you, Aisha. If you look at it, if it's equal, then it's equal. We know enthalpy changes of a reaction can be equal to enthalpy change of combustion, right, Aisha? Yesterday's class. So I don't care about combustion or formation for now. Here I care. In all the above examples, I was not talking about combustion or formation. It was just simple enthalpy changes. No multiply, divide, nothing. We were just tallying stuff. Yes, Afia is absolutely right. See, now since I've specified, and normally in the exams, you get questions like this, where they will specify it for you. So if I've specified that this is not the enthalpy change of the reaction, nah, I've not said this is enthalpy change equals minus 510, just like I was doing all the way here, plus 90, plus 33, nah, it's not said that. It has said formation ka, it's minus 510. So it's for 1 mole of ClF5 forming, that's the energy given out. 510, minus 510, that's the energy given out. But here you have 2 moles. So what should this be? It should be 2 times minus 510. Shouldn't it? Pretty simple. And Cl2 going into ClF3. So Cl2 going into ClF3. Again, the data that's given to me is not the enthalpy change. Nah, he's saying enthalpy change of formation, which is for 1 mole of ClF3 forming. Here you have 2. So what should I do? Please, again, these are my own values. I am just, making sure your concepts are clear. Please don't go on searching on YouTube, what is the enthalpy change? And then you come messaging me, said these values are incorrect. These are just made up values to fix your concepts. So Cl2 to ClF3. What is that? That's right here. But this is for 1 mole. See, formation is for 1 mole of ClF3 forming. Here you have 2. What should I do? 2 times what? Minus 328. Right? And this ClF3 to ClF5, I don't know, jack shit. So what is this? Direct route, which is 2 times minus 510, equals the indirect route, which is plus 2 times minus 328 plus x. What do you get? Minus 1020 equals 2 times 328. 2 times 328. Raima, it's the same thing. It's the same thing, Raima. Same thing. 2 times 328. Shabash. Do it. Minus 656. And this is x. Acha. And what do we get? Minus 1020 plus 656. What is this? What is this? Minus 364 kilojoule per mole. That's it. Acha. See, one of the student is saying, sir, shouldn't you divide the equation by 2? Sir, isn't this for 2 moles now? I'm just figuring out enthalpy change right here, kiddo. I don't care whether it's for 2 mole or it's for 1 mole. Here, I've not said, give me the enthalpy change of formation. I've said, give me the enthalpy change. Okay? It's not, I've not written formation here, have I? Have I written formation here? No. Okay? So I'm not writing formation anything. See, there is a difference between this and these two. Please try to understand that. Please understand this, right? That's why I'm not dividing by 2 here. If they wanted the enthalpy change of formation here, then I would divide it by 2. Yes, you are right. Why did I multiply it by 2? Because this energy given out is for 1 mole. It's for 1 mole of ClF3 forming. But here you have 2 moles of ClF3 forming. That's why I multiplied it by 2, Rima. Here you have, this is for 1 mole of ClF5 forming. You are going to give out this much energy, right? For 1 mole. Here 2 moles are forming. I'm doing it for 2. I'm multiplying it by 2. That's why. It's pretty basic. I've taught this in the last class, Rima. And this is the enthalpy change right here. I'm not writing formation or combustion, anything here. I just want to figure out the enthalpy change, right? Right here. Okay? Next. Next. Now, we're going to move on to some more ideas, some more examples, some more ideas. Let's do more and more ideas. Let's move on. So about question 7, NaOH solid gives me H, reacts with H2O liquid and gives me what? NaOH aqueous. Okay. Similarly, you have NaOH aqueous reacts with HCl aqueous and gives me NaCl aqueous plus Mahad, I'll cover everything, yaar. Relax, please relax. It's a long ass class. Okay. So again, NaOH solid plus HCl aqueous and gives me like NaCl aqueous plus H2O. And frankly speaking, we can't figure this out. This is what happens in the laboratory. I can't figure this out, but I can figure these two out. What exactly is this? What do you call this? You know, solid, a solute dissolving in water. What is this enthalpy change called, frankly speaking? What's this called? It's called the enthalpy change of solution. This is called what? Enthalpy change of neutralization, isn't it? I don't care, please. For now, I'm just going to give you enthalpy change. Enthalpy change. No form. I'm not writing solution, nothing with it. No faluda, shaluda with it, right? So this is just enthalpy change. I know you might be right that this enthalpy change of reaction would be equal to the enthalpy change of solution of NaCl solid. Yes, you are right. If you studied the last lecture, you know this stuff, but I don't care. I'm teaching everyone, am I not? So I don't care about this. So this enthalpy change is minus 43. This enthalpy change is about minus 57. What's this enthalpy change? Do it. Try to do it. Yeah. Try to do it. My turn to do it. Let's go. I'm gonna add my 3 boxes as always. Which should I take? Solid. Oh, solid, aqueous, solid. I'm gonna take this. This is repeating. Good stuff. Then on the right side, I have NaOH aqueous, NaCl aqueous right here. This is repeating. So this is effectively the first equation that I'm gonna write as my start and end stage. So start, end. Equation 3. If you want to write it, again, Mahar, I'm saying this for you. If you want to write it like this, it's up to you. If you want to write it like this, it's up to you. I couldn't care less, right? And sometimes you'll see in the margins, it's going to be written like this, but I want to declutter stuff. So NaOH solid is my starting point. NaCl aqueous is my ending point. This is effectively the third equation that I'm writing. You can write the entire equation in these boxes. I don't have space for it. And frankly speaking, I wouldn't write it. I'm a boring man. And this NaOH aqueous, this second equation is effectively your intermediate equation, right? So NaCl solid to NaCl aqueous, NaCl solid to NaCl aqueous. NaOH solid to NaCl aqueous, sorry. NaOH solid to NaCl aqueous. I don't know this shit. And then NaOH solid to NaOH aqueous, and then this to this. NaOH solid to NaOH aqueous. Solid to aqueous, that's minus 43. And this NaOH aqueous to NaCl solid. What is that? NaOH aqueous to NaCl aqueous, sorry, why I'm saying solid. NaOH aqueous to NaCl aqueous, that's minus 57. See, decluttering stuff. Saying again, direct root equals the indirect root. X equals minus 43 plus minus 57. So X equals minus 43 minus 57. What do you get? What do you get? Minus 100 kilojoule per mole. That's it. Asan, mushkil. Again, next. And let me tell you, I kid you not, these type of questions have rarely been tested on your exams, but they have been. I'll tell you what's most tested at the end. I first need to fix these basics, and then we'll do everything. Next question. Keep on doing it. I'll break your hands by the end of this class. Don't worry. That's my job. Everybody's going to be abusing me at the end of this class. Sir, you broke our hands, please. In the long run, you'll realize that it's good stuff. So we have to consider states. Frankly speaking, it's not about states. It's about choosing the equation. And it helped me choose the equation because I know out of these three, these two are the most repeating. And then out of these three, these two are the most. So it helped me choose my starting state and my ending stage. Afia? Yeah? It helped me choose my starting stage and my ending stage, which was this equation. And then the intermediate equation was right here. And then the intermediate equation was right here, and then the end equation was right here again. Right? So it just helps me choose. Acha, next. This is called decomposition of calcium carbonate. I can't figure out this even in labs. So we do this shit. We do this stuff. Calcium carbonate calcium carbonate goes into calcium oxide plus carbon dioxide. This enthalpy change, I don't know, but I know it's 57, not 57, it's I think minus 17. This enthalpy change is minus 195. This enthalpy change, I don't know. Somebody calculate it. Let's see. Shabash. Teri yaadein wo sari baatein. Okay, again, my 3-box diagram. I'll draw it. Start, end. Yeah. Perfect. Start, end. What should be my start state? See, this and this calcium carbonate repeating right here. Yeah. And should be my end state should be like calcium chloride right here. So which equation should I pick? Which equation? See, I'm picking out equations. This is equation 1 should fit in my start and end stage. This equation 1. If you want to write the entire equation, you can. I don't care. I'm just going to write this calcium carbonate as start and calcium chloride as end. It's not a chemical. You can write the entire equation. Calcium carbonate plus 2HCl gives me calcium chloride plus H2O. I'm saying this over and over again. I can't stress enough on this. It's up to you. You can write full equations. You can write half equations. I couldn't care less. I am just writing the chemical to declutter stuff. And frankly speaking, so should you. Okay. When you need to write the equations, I'll tell you when to do it, right? So calcium carbonate, and this is calcium oxide right here. I'm going to put calcium oxide. You can write plus HCl, 2HCl here. It's up to you. So calcium carbonate to calcium chloride. Do I know this stuff? Calcium carbonate to calcium chloride. Yes, this is minus 17. Calcium carbonate to calcium oxide. Calcium carbonate to calcium oxide. I don't know this stuff. Calcium oxide to calcium chloride. Calcium oxide to calcium chloride. I know this. This is what? Minus 195. Direct root, which is of minus 17, equals the indirect root. So minus 17 equals x plus minus 195. What do we get? X is equal to minus 17 plus 195, right? Plus into minus is minus, and then it shifts there to plus. X is equal to, what do we get? X plus 178 kilojoule per mole. And we know thermal decomposition is in fact endothermic, right? So it's 195, not 145. No, it's 195. Yeah, don't care about the values, guys. Don't care about the values. It's 195, not 145. Don't care about the values. If your concept is clear, don't care about it. ठीक है? This is 19 that I've written. 19 that I've written. Sir, I thought you wrote minus 19. No, it was minus 195. It's okay. If your method is correct, to hell with the values, please. Again, don't be grade 1 or grade 2 students. Come on. It doesn't matter that your values should tell you. If you've taken minus 136 here, your answer would be something else. I couldn't care less. My goal is to teach you how to do it. Calculations, अब मैं क्या करूँ? Right? Okay, next. An easy one. Carbon, which is graphite, plus O2 gives me carbon dioxide. And carbon, which is diamond, plus O2 gives me carbon dioxide. Again, 3-box diagram. Now this is pretty simple. Just given 2 equations. The end stage we know is carbon dioxide. End stage. That's the end stage. Start could be anything. Start and end. Start could be anything. It can be graphite, it can be diamond. Whatever you want. Whatever you want. Because it's just 2 equations. You can take diamond, you can take graphite, whichever one you like. Please don't say take oxygen. It's basically picking out an equation. You can pick this equation or you can pick this equation. Happy? So you can pick diamond or graphite. What do you want me to pick? I'll pick graphite. So carbon, graphite plus O2. See, I'll write plus O2 gives me this. And then this carbon diamond is my intermediate stage. It's not actually, I just named it intermediate stage. See? So this to this and this to this. Right? And this is plus oxygen right here. If you want, you could write plus oxygen. I couldn't care less, right? So this is about minus 9393 kilojoule per mole. This is minus 395 kilojoule per mole. And I want you guys to figure this stuff out. So, shabash. Graphite going into carbon dioxide, that's minus 393. Graphite going into diamond, I want to figure out this stuff out. And then diamond going into carbon dioxide, that's 3 minus 395. And figure it out. That's how they actually calculate stuff. So direct root equals the indirect root. Direct root equals the indirect root. It's plus minus 395. X equals minus 393. I can't help with calculator use. And this will give you x equals plus 2 not minus 2. Start point graphite क्यों लिखा? It's a very good question. Very good question. Which I said that you could write anything. So if you want to write carbon diamond here and plus O2 and you want to figure this out. You want to figure this out. This is x, let's suppose. You want to figure this out. Now this will be minus 2. You'll see. This is like graphite. And this is like carbon dioxide. In this, the question was figure out carbon graphite to diamond. Now my question is, see, that's why I picked out graphite first. See, graphite and graphite. But now my question is carbon diamond to carbon graphite. Happy? Now my question has changed. So first it was graphite to diamond, which I wanted you to figure out. Now I want to figure out diamond to graphite. So what should be my starting stage? Diamond and diamond twice. This should now be my starting stage. And this would be opposite to this. You'll see it'll be minus 2 now. Yeah, because graphite to diamond, if that's plus 2, then this should be minus 2. And you'll see. Diamond to carbon dioxide, what is that? Minus 395. Graphite to carbon dioxide, that's right here, minus 393. And this is x. So direct root equals indirect pathway. Plus, please add pluses because it's law of summation. Minus 395 plus 393. See, my question has changed. Please, the question has changed. That's why you're getting a changed answer. First it was what is graphite to diamond. Now it is what is diamond to graphite. See, graphite to diamond. Now it is what's diamond to graphite. This was part A, and this in fact is part B. Happy? Khush bash? Yeah. Acha. A couple of fun facts that could be tested in MCQs. Let me look at this. This graphite going into diamond, does this mean that the rate of reaction will be fast? Does this tell me that the rate of reaction would be fast? Graphite going into diamond. Graphite going into diamond, the enthalpy change is positive 2 kilojoule per mole. Would the rate of the reaction be fast or slow looking at this? Can this tell me anything about the rate of reaction? Plus 2 kilojoule per mole. I just want to check out your O-level knowledge. No, not O-level. This is new. This is something new. Can this tell me whether the reaction will be fast or slow? Can enthalpy change talk about rates? No, it can't. You all are right. No, it can't. Please understand that the size or the sign, the magnitude or the sign of enthalpy change does not tell me jack shit about rate of reaction. Nah. Never, ever, 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 ever. Rate of reaction is determined by the activation energy. So enthalpy change being positive, negative, wrong. Raima, that's what I want to fix. Raima is saying it will take longer maybe. No. Be it endo, be it exo, whatever it is. Sir, but endo hai to pata to chal raha. Nah. It's endothermic. That does not mean it's going to be slow or fast. Please, these are conceptual errors you need to fix. Endothermic or exothermic does not mean the reaction will be slow or fast. There are endothermic reactions which are fast. There are exothermic reactions which are slow. It's possible. Please, the sign or the magnitude does not tell me about the speed of the reaction. That has to do with activation energy, please. So this is one concept which can be tested in an MCQ. The next concept is, will this reaction occur? By looking at the enthalpy change, would this reaction occur? Would the reaction occur? If it's endothermic, would the reaction occur? Come on. Would the reaction occur? It's endothermic. So would the reaction occur? May mean nahi na. Raima, no may means. It does not mean anything about the rate of reaction, please. No may mean. Even if it's endo or if it's exo, no may mean. Okay? It's activation energy which has to do with speed. Nothing. No enthalpy changes. Nah. These are conceptual clarities that you need to have. Again, if this is plus 2 kilojoule per mole, does this mean per mole? Does this mean that the reaction will occur or not? Will this reaction occur or not? If it's endothermic, would it occur or not? Come on, guys. Somebody answer. Yes, no, yes. Please understand again that enthalpy changes has nothing to do with whether it will occur or not. Nah. Enthalpy change does not give you any idea of rate of reaction, and it does not tell you whether the reaction will occur or not. Some people are saying, sir, it's endothermic, so it shouldn't occur. Photosynthesis is also endothermic, so should we all die now? Should we all die? No, we shouldn't. It's endothermic. We know photosynthesis is an endothermic reaction. So should we all now live, climb on top of an edge and start killing ourselves because, it's endothermic, it will not happen? It happens. So there are endothermic reactions which do happen. There are exothermic reactions which do happen. Enthalpy change just tells you whether it's endo or exo. Nothing more than that. It does not tell me anything about this rate of reaction. It does not tell me anything about whether a reaction will occur or not. And these are very crucial things for MCQs. I teach you concepts. And why? Because whether a reaction will occur or not, you will study this in A2 chemistry. It has to do with Gibbs free energy. So this is A2 chemistry, Gibbs free energy. This will tell you whether the reaction will occur or not. Enthalpy change does not tell me jack shit about whether the reaction will occur or not, firstly. Secondly, enthalpy change, be it endo, exo, does not tell me anything about the rate of reaction. Right? Yeah. Now, it just tells you, Aisha, that if it's positive, that means energy taken in during bond breaking is more than the energy given out during bond formation. That's it. Right? Taken is more than given out. Right? So this is something you needed to know. Don't mix it with kinetic and thermal stability. Next. Done. So we're done with the most deadly examples for enthalpy changes. Now it's time to learn shortcuts. These are these are some of the most deadliest, my mom is going to kill me, she's going to say itni angrezi padhai hai. These are one of the deadliest examples, some of the deadliest examples that I've done, and you will rarely be tested on these deadly examples. Now, you will be tested mostly on shortcuts, and the way I'll teach it to you, you guys will be in shock and balk, right? So I'm going to take a 5-minute break because my gala is tired, and then we're going to continue, right? So shortcuts time. Okay, I'm continuing, guys. Inshallah, hopefully I'll finish it in the next 40 minutes, hopefully, right? So now is the time to learn what's actually largely tested in your exams. Okay, and what is largely tested in your exams? I call them the 4 shortcuts. The first shortcut relates with enthalpy change of formation. Right? Now, what is this all about? Let me teach you. See, reactants, when they go into products, there's going to be an enthalpy change, right? There's going to be an enthalpy change, isn't it? And I don't know this enthalpy change. But if I have data for formation, if I have the enthalpy change of formation for every single reactant and every single product, I can actually calculate the enthalpy change for any reaction. And frankly speaking, this is one of the best methods that is used in the entire world to figure out the enthalpy change of any reaction, because formation data is abundantly available with all of us, right? And we know formation has to do with what? With 1 mole of product forming, with one of a substance forming. I won't use the word product. With 1 mole of a substance forming from what? From its elements in its standard state, right? And we've studied this in the last class. And now you need to know a little about the last class. And I'll tell you, for example, if you have C6H12O6, what's the enthalpy change of the standard enthalpy change of formation for this? Can I write the equation for the standard enthalpy change of formation of C6H12O6? I can absolutely do that because I know which elements are involved. I know carbon is involved, which is in the form of graphite. 6 carbons are involved. Hydrogen in its elemental form is H2, right? In its standard state, obviously. And oxygen is O2. So you have 6 H2 involved and you have 3 O2 involved right here. This is basically the enthalpy change of formation of glucose, right? It's made from elements, all the elements right here, all the elements, good stuff, right? So we'll use all our elements, right, to make a certain reactant or a certain product, right? And so if I use this to my advantage, if I have the enthalpy change of formation for every single reactant and every single product, can I not actually calculate the enthalpy change of the reaction? Absolutely I can. And here is where you will see the first change in your diagram. What we'll do is, we know that its elements, like carbon ho gaya, hydrogen ho gaya, oxygen ho gaya. It's these elements which form reactants and products, right? It's these elements. So these elements will be forming reactants. These elements will be forming the other reactant. These elements will be forming a product. These elements will be forming another product. And you will figure out the enthalpy change through this, because you'll be given enthalpy change of formation. This will be the, or you could say, hey, whatever route you want to take, this will be the direct route, and this would be, or let me make it better, this would be the indirect route, and this would be the direct route. Doesn't really matter. You can call this direct, you can call this indirect, whatever, really doesn't matter. So you'll go from elements to reactants and to products, or from elements directly into products, right? So this is how we'll go. The direct route would be equal to the indirect route. Sir, what do you mean by all of this gibberish? Let me teach it to you through an example. And you'll understand what I mean. And we know, you'll know this. It's going to use last class information. So C4H10, let's suppose, reacts with 13/2 O2 and gives me 4 carbon dioxide, and it gives me 5 H2O, right? And I want to figure this stuff out, right? Now, how can I do this? How can I figure this stuff out? The examiner is going to give me enthalpy change of formation data. This is totally different from what you've studied above. This is now standardized data. So enthalpy change of formation of what? I will give you the enthalpy change of formation of carbon dioxide, which is what? Or let's start from the left side. Let's start from C4H8, H10, C4H10. The enthalpy change of formation of C4H10 is minus 127 kilojoule per mole. The enthalpy change of oxygen is what? The enthalpy change of formation for oxygen is what? Please, yesterday's class, please, is what? 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 It's zero. We know enthalpy change of formation for any element is zero. For any element is zero. And I went into so much detail for it. We call this a null reaction. Remember? A null reaction. This is like saying, hey, O2 gas is going into O2 gas. It's like saying 2 equals 2. So enthalpy change of formation for any single element is a zero. Don't use the word except for allotropes. Fatima, graphite and diamond are totally different. So if you want to talk about graphite and diamond, they're different things. And yes, I covered that as well. Thank you. So this is zero. Oxygen always will be zero. And that's why the examiner will be very sneaky. He'll want to test this, so he'll never give you this. He'll think that you should know that enthalpy change of formation for oxygen is zero. It's an element, right? Next, for carbon dioxide, I need to find, is given to me, minus 394. For H2O, liquid, this is liquid, right? Enthalpy change of formation, liquid. And here, this is gas, and whatever this is, I don't care. And this is, let's suppose, minus 286. Now, how do I figure this X out? And it's pretty simple. I will use the same idea of my 3-box diagram. Same idea. The only thing that changes is that I have elements here, right? I have elements because elements will be forming this stuff, 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 right? And you don't even need to write elements. No, you don't. I know that this is made from carbon and hydrogen. This is made from, I know this is oxygen going into oxygen, so its enthalpy change of formation is zero. This is made from carbon and oxygen. This is made from hydrogen and oxygen. I couldn't care less. I don't want to write these elements, right? And so I know that I write my reactants and products here. And the idea to it is to write the most populated equation right here. That's why I used to tell you I'm writing the equation. I'm not selecting one chemical, it's the equation. So can we write the equation? C4H10 plus O2 is what? 13 over 2. 13 over 2 O2 and gives me what? This is called the most populated equation. So at start and end, this is my reactants. These are my products. I'm going to write the most populated equation right here. That's the only step. So 4CO2 and 5H2O. 4CO2 plus 5H2O. Right? Now, it just starts to unfold. Because you tell me, what's the enthalpy change of formation of this fella right here? Elements which would make C4H10. And I'll write it to you. How would C4H10 be made? Carbon solid plus hydrogen gives you C4H10. I couldn't care less. I wouldn't write carbons and hydrogens here because it doesn't really matter, right? Because it's for 1 mole of this forming, right? It doesn't matter how many hydrogens you have, if you use 4 carbons, if you use 5 hydrogens, it doesn't really matter because at the end, enthalpy change of formation is for 1 mole of a substance which forms. Crystal clear. And it is 1 mole. And what is the value that's being given to me? It's minus 127. Minus 127. That's it. What's the enthalpy change of formation of oxygen? It's 0. It's a null reaction, right? Right? And this is effectively just 1 arrow. We write 2 arrows for our own ease, but it's effectively just 1 arrow. Please understand, these are not multiple arrows. It's just 1 arrow and goes like this. Like this. Right? And here, elements go into carbon dioxide. Again, I can show it to you. That carbon solid reacts with oxygen, gives you carbon dioxide, and you have 1 carbon and 1 oxygen to give you carbon dioxide. Doesn't really make a difference. The enthalpy change of formation for carbon dioxide is minus 394. And this is for 1 mole, isn't it? Because enthalpy change of formation is for 1 mole of a substance which forms. And this is minus 394. How many moles are forming actually? How many moles are forming? So this is irrelevant for me. In enthalpy change of formation, this is irrelevant. I couldn't care less how many carbons, hydrogens, oxygens are used. No, I only care about how many moles of this form. Because enthalpy change of formation is for 1 mole. Here you have 4 moles. What should I do with it? So I should multiply this fella with 4. Isn't that true? 4 times minus 394. That's it. Because this minus 394 was for one carbon dioxide forming. You have 4 CO2s forming. That's it. Next, elements into H2O. Again, if you want me to write it for you, I will, but after this I wouldn't, because it's irrelevant. It's irrelevant. You don't even need to write it. And here you have half oxygen. Doesn't really make a difference because it's for 1 mole, 1 mole. And what is that value given to me? It's minus 286. But here you have 5 H2Os. So for 1 H2O, it was minus 286. For 5 H2Os, it's 5 times minus 286, isn't it? And now it's just, imagine this as a single arrow, imagine this as a single arrow. How would you move if this was just a single arrow? You would move like this would be your indirect route, and this would be your direct route, right? Start to end, right? This was the indirect route, or you could also write the route here, but I like it like this. I like it like this. So it's elements going into this, and this directly going in. See, this is how my arrows are leading me. Tuck, tuck, and tuck. That's it. So let's do it now. How do we calculate x now? It's what? It's minus 127 plus x equals, see? Minus 127 plus x equals, and here I should put brackets, right? Because it's law of summation. And then equals what? All of this stuff. So what is this equal to? 4 times minus 394 plus 5 times minus 286. And this is always so beautiful if you have formation data available. So that's it. That's literally it. Just write the most populated equation right here, and from elements tuck, 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 go into this, go into this, go into this, go into this. Right? And frankly speaking, everybody should teach you this because it's written in all the books out there, all the books. And these are the shortcuts you need for MCQs and all. There's also another way to do it, but it's so lengthy that it's too lengthy. So I don't care. So what do we get x as? Please help me out. Can you guys sum all of this for me? What is this? What is the sum of all of this? Somebody help me out. It's minus 3006. I hope you're right. And then it's plus 127. Can you guys tell me? And so you can calculate x as what? Minus 2879 kilojoule per mole. That's what x is, right? The enthalpy change of the reaction. My question to you guys is, what is this? What is this value? X is equal to minus 3006 plus 127. And this is what teachers will teach you. And I don't like this. I don't even want to teach you this. But again, it can be tested in the MCQ. So I would teach it to you. This is the enthalpy change of formation of products, isn't it? The enthalpy change of formation of product, the enthalpy change of formation of product, isn't it? This, all of this stuff. So I've just added them, right? The enthalpy change of formation of product A, product B. So can I say this is the sum of the enthalpy change of formation of products? Can I say this? It's the sum of the enthalpy change of formation of products. And what is this? This is the enthalpy change of formation. The enthalpy change of formation of reactants. Yeah? And this is the formula that you guys, and it's the sum, right? This 127 is the sum. This is the formula that you would have been taught in the classes. And it's absolutely BS. I hate this formula. No need to learn these formulas and rote learn them. It's pathetic. You have Hess cycle, it's a piece of cake. And why is this a minus set? There is a positive sign here. I'll tell you. Because in formulas, this negative sign is exclusive. It's not the negative sign of this 127. And I'll prove to you what I mean by this. See, what is the enthalpy change of formation of products? It is the sum. It is what? It is minus 3006, right? And then minus the fact, minus what? Minus what? This minus 127. Minus 127. So minus 127. And that's why it ends up as A plus. So this negative right here is exclusive of this negative. And that's why I hate formulas, because they'll confuse you to your core. Right? So this is, a formula, and this is enthalpy change of reaction, isn't it? So you could have also come up with a formula like this. The sum of the enthalpy change of formation of reactants plus the enthalpy change of reaction equals to the enthalpy change of products, formation of products, right? So you could have also done this stuff. Enthalpy change of formation of reactants. This is only for MCQs. Equals, and you can derive it from Hess cycle. See, this plus this, See, I have never rote learned them. I write my Hess cycle and then I write the formula from it. So this plus this right here equals the enthalpy change of formation, the sum effectively. You want to write sum, you don't want to write sum, it's up to you. But equals the enthalpy change of formation of products. And this is what I've done. Direct route equals indirect route. See, and that's why you get this formula. Yeah? And you can check this out. This X is enthalpy change of reaction. And see, if you shift this right here back, it forms this fella. So these are some formulas, but I couldn't care less, and I will advise you all to not rote learn them. But if you know your Hess cycle and you know how you go, this is the indirect route, this is the direct route. So enthalpy change of formation of reactants plus this equals this. See, it's so easy, and then you can mingle with the equation as much as you want. Done. Let's do a couple of questions for this shortcut, right? Let's do it. So, question: enthalpy change of formation of Fe2O3, and see, this is completely different from what you've studied above. Above, what we studied was no standard enthalpies were given to it. It was just enthalpy change, and we were using Sir-Suleiman's method. Now this is a pretty easy thing to do, right? It's just you're given standard things, so you could even write the equations. But I couldn't care less. I wouldn't write the equations for it because I already know. I already know how to do it. It's all formation data is given to me. So how should my brain work? This is very important. This is 9, please, not 4. If you want, I will fix this. It's 9, 4, right? How should my brain work? My brain should work, and my question is find Fe2O3 plus CO going into Fe plus carbon dioxide, and this should be a 3. Let me fix this 3. This should be a 3 and this should be a 2, right? Find this. So how should I do it? I'm given formation data. And this is how my brain should work. Formation data, 3 box. And what should I do? Formation. Form this, and tuck. That's it. So I'm going to draw my 3-box diagram. Write the most populated equation. Start. And this is effectively the most populated equation, what they want you to find right here. The one that has the most reactants and products, right? I'm going to take this up. The most populated equation, Fe2O3 plus 3CO. See, these are equations which we were writing even above, but I couldn't care less because it was cluttering the boxes for me. Here, I'm going to write them, right? So this is what I need to find. And here you have your elementariness. So Fe2O3, delta H formation for 1 mole. And you have 1 mole. What is this? Minus 824. Minus 824. Similarly here, into carbon monoxide. Carbon monoxide's enthalpy change of formation is a minus 120. But how many carbon monoxides do I have? 3. See, it doesn't matter how many moles of elements were used, how many carbons were used, how many of... No. What matters is formation has to do with what is being formed. And this needs to be crystal clear in your brain because it'll confuse you when you do combustion. So it must be crystal clear in your brain that, hey, formation is for this forming. So if carbon monoxide, 1 mole of this would form, this much energy would be given out. And it's 3 moles right here. So I'll multiply it by 3. That's why I don't even really write the elements here because it just confuses us. So do you mean reactants by the most populated? No, most populated equation means the one that has most chemicals. 1, 2, 3, 4. If you write all of the other equations, it has 3 chemicals in it. You can write it, if you want to write it, it's Fe plus O2 gives you Fe2O3. I'm not going to balance it right now, but this is C plus O2 gives you CO. See, here you have 3 chemicals everywhere. And here you have C plus O2 gives you CO2. You can write these equations if you want, but it's just going to be a waste of time because I already know. She's gonna get real, right? So this into minus 110. Elements into iron. Yes, iron. What is iron? Iron. What is the enthalpy change of formation of iron? Why hasn't the examiner given it to you? It's in its elemental form. It's like saying, hey, iron, solid, goes into iron. So it's like saying 2 equals 2, 3 equals 3, 4 equals 4. Pathetic. So it's 0. You don't even need to write 0. Just skip it out. Carbon dioxide is given minus 349, but it's for 1 mole. Here you have 3 moles of CO2 formed. See, formation is for 1 mole of the substance which forms. And this substance, it's for 1 mole of carbon dioxide forming. Here you have 3. So what should I do? 3 multiplied by what? Minus 394. And so the indirect route equals the direct route right here. So it's what? Minus 824 plus, and I'll put these brackets here, plus 3 times minus 110 plus x equals 3 times minus 394. Somebody help me out. Sir, please stop, unable to focus anymore. Dead body, you can watch. Dead body, you can watch the recording later on, kiddo. I have to teach. It's my class. It's you are all sitting in my live class, which I teach twice, thrice a week. So I'm sorry. You can watch the recording later on. I have to finish my class. So what's the value, guys? What do you get? Please don't give me the final answer. Just give me the final answer is what? Minus 2828 kilojoule per mole. I hope it's right. Sum all of this up, shift it to the right, and that's it. Bougie. Next, recording will be available on YouTube. I can't promise that, dead body, but hopefully it will. Hopefully, I can't promise it. I can't promise it. Promise it. So the examiner learned. Now, listen. This is so important. This is so important now. It's so important. The examiner learned that students are now getting very clever. Students are getting very, very clever. Very clever. And how did he know that you are getting clever? He knew that he is just giving you formation, and you're like, oh my God, let's do this. No, let's do this. It's pretty easy, simple. And so he thought that students have started rote learning stuff. So what he did was something peculiar, but something very interesting. He threw a curveball at you. It's very, it's very simple, but he threw a curveball at you. He did this. Copper oxide plus aluminum gives me like copper plus Al2O3, right? And if I balance this fella for you, this is 3, and this is like 2, and this would be 3, right? If I'm not wrong. And so what he did was he gave you this, and he said figure out X if, and he gave you a bunch of equations. Copper half oxygen gives me copper oxide. Aluminum plus 3/2 oxygen gives me aluminum oxide. And what he did was he said nothing else. He said the enthalpy change is minus 155. The enthalpy change here is minus 1669 kilojoule per mole. Now, it's just 30 more minutes, Hasib. Now, the thing is that you might think that why not use Sir Suleiman's method? Before using my method, now these are the things which you should keep in mind. Before using the first questions that I did, there was a reason behind doing all of that, because that's really tested. But before you use my method, you need to use your brain a little. And which brain do you need to use? You have to first check whether it's formation data or no, whether it's just enthalpy change. And when you check it out, you will see something. And this is a 2 here. Okay, sorry. Thank you. This is a 2 here. When you check the data out, it's 1 mole of a substance forming right here. So what is this? This is effectively the formation data. This is effectively the formation data for copper oxide. So before using my method, think if there's formation data available. And that is it. It's the formation data of copper oxide which has been given to you. What is this? It's 1 mole of a substance which is forming. So effectively, this is the formation data of aluminum oxide that has been given to you. And that's all you needed. So you now know that instead of writing this in the examiner used to do this a lot. Instead of this, examiner thought students might rote learn these things. So what he did was he actually gave you formation equations. And so you just needed to figure out, hey, this is formation data. Oh, no bueno, easy peasy. I'm just going to draw my 3 boxes and do it the same, use my same shortcut, which is what? Right, the most populated equation right here, which is this. This is unknown, right? And the other 2 are just formation data. So write the unknown right here, the most populated equation. Unknowns are usually the most populated equations. So that's how many copper oxide? 3 copper oxide plus 2 aluminum. See, now is the time for, broadening your brains. 3 coppers plus Al2O3. That's unknown. And he literally gave me formation data. So I can just write elements here. Copper oxide's formation data is given. He gave it to me in the form of an equation, which is minus 155. So minus 155 into 3, because it's for 1 copper, right? Similarly, aluminum formation data 0, it's in its elemental form 0. Enthalpy change of formation for elements is 0. It's a null reaction, no chemical change. It's like saying 2 equals 2. That's it. No matter how many moles here are, doesn't make a difference. It's like it will also form from 2 aluminum would make 2 aluminum. So it's like saying 2 equals 2, 1 equals 1. So don't be confused by the moles, please. Similarly here, you might say, hey, 3 times copper. No, copper is its elemental form. 0. Nothing. No, bueno. Nothing. Here, see, these are the things which the examiner will get you confused. With these 3s, these 2s, always look at what's given. It's element. It's like saying enthalpy change of formation of 3 copper is 3. These 3 copper is what? It's made up of 3 coppers. It's like saying 3 equals 3. Right? So please, you should have taken the last class to understand this for elements. And here aluminum oxide is given. What is this? This is -1669. So before you even use my method, that was for more complicated questions where you couldn't figure out stuff. You just stick to shortcuts. So -1553, this is the indirect root. This is the direct root. So you need to reach the end, right? This is the start and this is the end. So you need to reach the end. How do you reach the end? Like this. So plus x equals what? -1669. And so what do you get? -155 into 3 plus x equals -1669. X equals, somebody help me out. Somebody please help me. 1204 kilojoule per mole. I hope you're right. How easy is this? And this is what you're mainly tested on. These type of questions. You want me to do one more? One more for formation. Enthalpy change of formation. One more, sir. Acha. N2H4 plus like O2. This is X. If you're done with your next, move on to the next. If you're done with your next. Now I won't confuse you, so I'll just give you the data. If you're done with your next. Raima बहुत ज़्यादा रहता है. Sorry guys. Sorry. I just saw a reel, yaar. I'm sorry. I just saw a reel. Please. Bakshish. Give me some bakshish. How many of you guys are new? Like, how many of you guys have never heard of me before? Yeah? Solve this. If you're done with your next, sorry girls, sorry guys. थक गया हूँ यार मैं. My energy is going beep like this. So the most populated equation is right here. So N2H4 plus O2. And did I balance this stuff out? Is N2H4, this 2H2O, isn't it? It's 2 here. And then that gives me N2 plus 2H2. And now the above questions, the ones that I did in the start, they should also make sense. That I'm actually picking out the entire equation. That was just a shortcut. This is 0, it's 0. This is plus 51. And this is anyone into 2H2O. This is for 1 H2O, right? Enthalpy change of formation. So you have 2 H2Os. And so the indirect is equal to the direct. It's plus 51 plus x minus what? Minus what? Minus 572. X equals minus 572 minus 51. Whoop. 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 That's it. Easy. सबर करें अभी बहुत और रहता है रायमा डेवलप स्टैमिना वैसे भी कल परसों तरसों 3 days holiday. Enjoy the holidays. Jet to holiday. Some reels, and let me show you some pictures now. Enough of me writing. Let me show you a couple of pictures. You're done with your next. See, this is Hess cycle. See, Hess cycle. Indirect root equals indirect roots. It's the sum. You could go from this to this or this to whip and whip. Yeah. Show you some more pictures. Just look at pictures. Formation is khas. A little more is remaining. Chill. If you're done, move on to the next. This is what I've actually taught you. This is what I've taught you. Right here. This is always when formation data is given. Right? Happy? Formation data is given, and a tuck, can a two, can a d, can a da 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 d. Yeah? Let me show you some more pictures. तेरी यादें वो सारी बातें तू ही बता कैसे भुलाऊं. This is one more. Now, in this picture, you'll see that instead of them doing it like this, whip and whip, they've done it like this. They've gone toop, 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 like this, right? They've gone whip. This is the indirect route and this is the direct route. But then you need to be careful. See, you are going against the arrow. And if you're going against the arrow, if you are going against the arrow, whatever you've written here, whatever, if you wanted to go like this, if this is the start and you said, I want to go from start to end like this and then like this, it's up to you, right? So if you thought, and please, this is so important to understand right here, if you thought that this is the, I'll take, obviously, you normally go from start. From this, I said, hey, elements to this and this. But if you want to actually go from start to end like this and then this, then what would you have done? Start to end is X, and that is equal to this fella. But now if you were to go like this, then this, you are going against this arrow. So then this plus 51 would be negative, because elements to this is plus 51. This to this would be negative 51. Then it would be negative 51 plus 2 times negative 286. And the answer would be the same. So it doesn't matter. If you're going against the arrow, yeah, then you'll have to make sure of this thing to flip the sign as well. See, here I was just going poop and poop, and this you could also go direct route and whoop, indirect route. So same thing. And to be on the safe side, what I did was I just went like whoop and whoop, so I don't have to flip signs of any arrows. I don't have to go against any arrows. You know, see. If you're done with it, if you're done with it. And this is what we've actually done right now. See, it looks so complicated. This is the example which we just did right now. See? Enthalpy change, this is 0, that's 0. He's written this, but it's 0, obviously. This is 0, obviously. And this weep, weep, weep. See, he's written elements. I don't care. I'm not writing. I'm just going to label it as elements. Teri yaadein. And if you want, this is actually the proof for the formula. You know, if you want me to add it. Sir, please add it. Here you go. If you're like a book geek, if you're like a geek, a kitabi kida, you can see the formula, right? This is like the derivation of the formula that I showed you. You know, instead of using actual values like I did here. See, here I used actual values to prove the formula to you. Like this, see? Delta H reactance of plus this is equal to enthalpy change of products. This is literally proven through this chemistry right here. See, enthalpy change of a reaction is equal to products minus reaction. If you shift reactions there, it's enthalpy change of reactants, reaction plus reactants equals products. Right? Done. So this is actually proof for it. You don't need to know. Sir, arrow change करने से आंसर गलत आ रहा नहीं रायमा. It's impossible. It's impossible. You don't change the arrow. The arrow is like this. This is elements. You don't change it on your own. You imagine it going from this to this. So if you go against the arrow, that doesn't mean you change your arrow. The arrow is from elements to this. But if you want to go from here to here, that doesn't mean you change the arrow. No, you just change the sign, which is plus 51 ki jagah, you write minus 50. So minus 51 plus 2 into minus 286 equals the same answer, Raima. How is it galat aa gaya, yaar? If you add these, what do you get? Minus 51 into 2 in plus 2 into minus 286. It's the same. How is it galat? How is it galat, Raima? Please answer this. How is it galat? No, first answer this. How is it galat? How is this and this galat answer? It's the same. instead of writing, I'm going against the arrow. This arrow points here, and this was plus 51. I'm going like this now. So it should be minus 51 and then plus this fella right here, because this is with the arrow. I hope this is clear, Rama. Please give me a yes, give me a nod. Right? Here it was just plus 51 plus x equals this. X से पहले minus था. This is not x, this is multiply sign. हो गया सही? Is it fixed? Please